Okay, so this week in general, we started talking about modeling. So before this week, we were talking about mostly coding, right? So we wrote code. Now, software engineering is much more than that, just code. So creation of a software system is a process, and we refer to it as the process of, we call it software development lifecycle. Okay, so that's what SDLC stands for. So it is very important for you because you are training to be an engineer. So an engineer in one field plus an engineer, software engineer with a particular focus on AI systems, and that's the software aspect. But that's still you focus on AI systems, but it's a software system. Okay, so the creation of the software is a process that involves much more than just writing the algorithm or writing the code or writing a script. Now, a lot of people in the AI field focus too much about the scripts and how you run the scripts to get the results. Okay, but the creation of the system itself. Now, something like ChatGPT, for example, it's not just the algorithm, right? The algorithm is a very important aspect, but there are so many aspects that is the creation of the software system surrounding the algorithm that allows the algorithm to be useful, right? So that's what we are trying to understand today, the software development life cycle, and how, like, the kind of thinking that you need to have when you are creating a software system, okay, regardless whether it's AI or not. So when we say software engineering is much more than just coding, we're talking about problem solving. So you have a problem. It's not just writing code. You have a problem that you're trying to solve. Okay, so you need to understand that problem first, and you need to figure out what is the best solution for that problem before you start creating the solution. Okay, now you engineer the system based on, so that all that is the mental process. It's not, you didn't touch any code. Like most of the work done, or the most important work done, is done in your head. It's not on the keyboard. Okay, so there's a lot of problem solving that is needed. A lot of modeling, obviously. Modeling is needed for communication, and it's also helpful, even if you're working on your own. It's very helpful to organize your thoughts and understand the problem better. Okay, so modeling is a very important aspect. Knowledge acquisition, most of the time you are creating a system for some field that you're not familiar with. Now here, when I say this software engineers, the pure software engineers, almost 100% of the time, maybe not 100, 99% of the time, you're creating a software system for a problem that is not part of your expertise. So if your expertise is only software engineering, then you need to create systems. Well, of course, you can create the system that can be used in software engineering, but most of the time you're creating systems to be used otherwise, other different applications, right? So you need to understand the problem. So knowledge acquisition is very important. Now you have a privilege, the students in this program, you have a privilege that you are building expertise in one field in addition to the field of software engineering. Okay, so that gives you a major advantage in that field. But it doesn't mean that you don't need knowledge acquisition, because like this expertise in your field, you need to put both of them, your engineering background and the software engineering background, together to solve a problem that is most likely new to you. Okay, so there is a learning process that is always ongoing when you create a software system. And then there's a rationale management. The management aspect is very essential. There's no room for this course to talk about the management of the software system, but in the next project course, we will include what is agile, what is Scrum, how to manage software, the creation of software system. But that's also crucial in the creation of the system. Okay, so in this course, we're going to talk about the several components or the several activities, but we're not going to talk about the management yet. Hopefully in the next course, you should be able to learn about it. Okay. Now, yesterday, I think it was yesterday or the day before, I don't remember, when we started talking about UML the day before, my first session. Now it was introduced as a standard, and there was like serious attempts to standardize the activities in software engineering, but these attempts proven non-successful. So that's why the agility, or we wanted to introduce more flexibility so that we would be able to handle software system. Unfortunately, some people took this to the extreme, to the point that they want to go back to the ad hoc. So the ad hoc is just like, okay, we have a problem, let's write code. Without proper management, without proper thinking about the problem. Okay, so they said, okay, following the standard didn't help, so we scrap up all the modeling, all the planning, all the documentation, and we just go back to the ad hoc approach, which also was not successful when it started with software. So software started as ad hoc, and then they went to one extreme to make it an engineering discipline, so it make it standardized and disciplines, and both extremes are wrong. We want to find the blissful point between both of them. Okay, so even though we have flexibility, and all what we learn from the modeling and from the activities in software development lifecycle are still all recommendations. There is nothing forced, but still we need to have this process managed as much as we can without rigidity. Okay. So now you see the why do we need activities? We can't go back to the ad hoc as it started and just ignore all the activities in the process. Now here's a real challenge when you're creating software system. You have a problem that is part of a real system, a real world problem or a real system. Now part of it, you want to create a computer system that would help it. Now you describe the problem with the language that is described in the real world or in the real system. So that's like human language, English or whatever human language you describe. Now the problem with the human language is that it can hold multiple interpretations. So when you have a problem statement, you may have multiple interpretations for that problem statement. Every word could be understood with different meanings, and we have different words, one sentence. If you plug different meanings for the different words, you get different meaning from the sentence altogether, right? So that's the problem with the human language. Description of the problem is vague and ambiguous and can be understood in different ways, and that's actually pretty much the main reason most of software systems used to fail. A lot of misunderstandings, different interpretations. The developer ends up implementing something that is not useful to the customer or not useful to the problem to begin with. Okay. Now, on the other side, what we are trying to reach at the end, so we have a problem described in the vague language. What we want to reach at the end is something written in a language that is a programming language that is not ambiguous and it is not subject for interpretations. When you write a line of code, there are no two meanings for that line of code. There is exactly one meaning. And that's what the processor is going to do, right? Now, how can you move from multiple possible meanings to exactly one meaning? As a developer, as a software developer, what would you do? You have a problem described, yes? Right? Yeah, that's the right thing. But at the end, you need to choose one of these meanings, right? Now, choosing this one of these meanings that happens without proper modeling and proper continuous feedback means that you may choose something that is not what is intended. And that's a common problem. Okay? So to move from multiple meanings to one, we have to pick one. Now, which one? That's why we need multiple steps in order to move from the ambiguous to the specific. And every step we create models and we get feedback, and then we update our models, and then we move on to the next step, and so on. Okay? Now these steps, like we can group them into three categories: the requirements group, so that's analysis, elicitation, and analysis, and then there is the design, and then there is the implementation itself, and then we end with a computerized system. Okay. So that arrow is just to describe the direction we want to go into. It doesn't mean that it is linear. It is actually not linear at all. Oftentimes you want to go back from one step to the other in order to fix it, or like as you go through the system, your understanding of the system would be enhanced, and you would need to go back to previous models and fix them or update. Okay, so the process is not linear. This line doesn't indicate linearity. It just indicates the direction that we want to go with. Now, actually, it is the process is described as a cycle because it's never ending, and this is part of the cycle. Now this is a development cycle. Now there is what is popular now is the DevOps cycle, or development operations cycle. It's outside of the scope of this course, but this is just part of what needs to be done. Now there is another, if you look up DevOps, it is more like an infinity. So there's just a development cycle, and then there is the operation and deployment cycle that now are open with each other. So it's more like a infinity cycle.